Hello, my name is Jared Smith, and I am a technical product specialist at Adams. I support everything around valves, actuators, and general pneumatics. It's going to include also vacuum systems for material handling. Today, I'd like to walk through a vacuum training that I put together, just to kind of walk through the vacuum theory, common components used in these systems, and some best practices. So, jumping into vacuum theory, I feel like when most people hear the word vacuum, they think it's black magic. And I'm here to tell you it kind of is. Um, People like to think of vacuum where if you're just at your house, you have your vacuum cleaner, right? That's probably the most common, vacuum application that people see on a day-to-day scenario. And all it's doing is just, sucking up dirt, right? It's sucking up dirt, debris from the floor. And, rightfully so, people think that's how industrial vacuum system's working. It's just pulling on the part, and that's how it's creating some kind of a hold force to handle parts. While that suction, that flow, we'll call it, while that's part of the process, that's not the whole story. There's actually a lot more going on behind the scene here to handle parts. And with that is the idea of atmospheric pressure. So atmospheric pressure is the pressure all around us. It's transmitting in all directions and always present. At sea level, it's going to be equal to 14.7 psi. People are often familiar with the terms PSI gauge or PSIG, and also PSI absolute or PSIA. So that's where that's coming into play. Many of the gauges that we use on a day-to-day basis, they're working off of PSIG, so they already account for that 14.7 psi that's present at atmospheric pressure, and that's the theory that vacuum systems use in material handling. So you're going to create a volume that's lower than the atmospheric pressure to create the holding force used to handle parts. And because of this, you have a very low margin of error. You just have that 14.7 psi to work with from atmospheric pressure down to absolute value, or I'm sorry, to absolute vacuum. So it's pretty tedious, and that's why people may have more issues than they anticipate with the vacuum system, just because you have such a low margin of error. So this is just reiterating those theories more with different units to kind of visualize what's going on. So on the right here, this dotted line is atmospheric pressure, and from there down to zero, zero vacuum or absolute vacuum is kind of the range into which we're working with in a vacuum application. On the left here, you see common units to depict vacuum. The most common is going to be the negative kilopascals or inches of mercury or percentage of vacuum. The negative kPa and the percentage of vacuum are kind of one and the same, because negative 101.3 kPa is also equal to 100% vacuum. So those are kind of interchangeable. So that's where you'll see the negative kPa often used. So vacuum flow and vacuum level. So the vacuum flow, as I mentioned in the vacuum analogy, like a traditional vacuum cleaner application, the vacuum flow is the amount of air that a vacuum pump or a vacuum system can draw out of a given volume of space. So common units for this is normal liters per second or standard cubic feet per minute. The more flow you can have, the more volume that you can extract the air out of, the faster you're going to hit certain vacuum levels. So that's going to lead to higher productivity. You're able to handle parts quicker and get them to a state where then the robot or a pick and place, whatever the vacuum system is mounted to, can actually handle the part. Flow, higher vacuum flow can also help offset cup wear because you're not applying as much force to the cup. Where vacuum level is the actual pressure below atmospheric pressure that the system is reaching. You cannot have a low vacuum level and a low vacuum flow, or high vacuum flow and a high vacuum level. So that's depicted here by this graph on the left. So when you have a vast amount of air to evacuate, you can do it pretty quickly. But as you reach deeper and deeper levels of vacuum, you simply cannot evacuate it fast enough, right? It starts to slow down, and it takes more time and energy to evacuate that last bit of air to reach deeper vacuum levels. This graph on the right is a good visual to see the different levels of vacuum from 0 to 20%. That's just low level vacuums. That's probably what your vacuum cleaner at home is running at. And then industrial vacuums are 20 to, we'll say, 99. You're typically quite a bit lower than that, but it can be up to 99%. And then if you're at 99% to 100% vacuum level, that's like a scientific or some kind of a process vacuum in a research lab environment typically. So how do you generate that vacuum? So in most industrial material handling applications, you're going to use an ejector, so either a single stage ejector or a multi-stage ejector. The single stage can either have the high flow or deep vacuum. You can't really have both there. It is going to be a little bit of a lower cost solution, maybe more compact and not generate as much heat, but it's going to be much more noisier, and it's going to be much less efficient than the multi-stage equivalent. It's going to use about 40% more air than the multi-stage. So these ejectors, they actually use compressed air to create vacuum. So the compressed air is going to come into the system here on the left, enter the ejector, and it actually goes through a venturi to speed it up, which creates a void or a space that's in a vacuum condition. And then at the other side is the exhaust from that compressed air, speeding through the system. The multi-stage ejector is a series of ejectors where you can have the first nozzle be small, so you can reach deep vacuum levels with it, where the last nozzle is a larger one for higher flow, and then you can have some intermediate ones in between them that is somewhere in between. So this gives you a much better product, and it's going to be more efficient, more reliable, much more modular and configurable. And you also have a much lower energy consumption, with the multi-stage option. It's also going to be quieter. So it's the same idea. You're going to come through with the compressed air. It's going to hit the venturis and then create an area of vacuum. So in most applications these days, you're going to want to default to the multi-stage ejector, but there could be some niche applications where the single stage still makes sense. So going back to that graph where you saw the different vacuum percentages, it's usually not very efficient to go beyond about 60% of vacuum. Beyond that, you just have to take a lot of time and a lot of energy to get to those deeper vacuum levels that aren't going to be really necessary for most industrial automation applications. You just don't have the time to wait around in the fast cycle time machines to allow the system to come to that deep of a vacuum level. So in most applications, just using a larger cup at a lower vacuum level is going to be a more energy efficient and cost-effective solution to get the holding force required for that application. And less force on the cup also equals longer life. So you're not creating a scenario where it's a big pressure differential and you get higher forces being applied to that cup, and it's going to make it wear much faster. So this is just kind of a cool little graph showing you the different types of ejectors and their flow versus vacuum level, and like how quickly it can get to those levels. So as you can see here, the multi-stage is it has pretty quick evacuation of that air. It's quite a bit of volume, but then it kind of steadies out, and then it's able to reach deeper vacuum levels. So suction cups. Suction cups are essentially like the actuators in a vacuum application. They're the ones using that energy. I guess technically it's the one that's using the atmospheric pressure because of the low pressure within the sealed environment. It's actually doing the work. It's creating the holding force on the part to handle it. So as I mentioned earlier, you're evacuating that area in that space under the cup, and then these arrows here on the right are depicting the atmospheric pressure that's pressing in all directions on the cup, and then also the part against the cup that's creating that holding force present to do the work required. When sizing systems, the holding force of a cup is going to equal its area times the vacuum level the system is at. So because most applications are going to use a round cup, but this still applies to other shapes. But since the area of a round cup is pi r squared, since the area is squared, just increasing the size of the cup can drastically increase the holding force that it can produce. So it's going to be much more efficient to just increase the cup a little bit than try to reach a deeper level of vacuum, which is going to again take more time and more money to do. And I will say, when in doubt, testing is crucial. We're about to walk through a lot of the more common cup types, and there's a lot of options out there. So we're a partner of PIAB. So PIAB actually has a factory up in the Northeast where you can send parts and products for them to actually have an applications engineer go test your product and see what type of suction cup is going to work best. There's a lot of options. And as I mentioned, with little margin, it can be kind of finicky to really nail down a great solution without testing it first. So suction cup shapes. As I mentioned, the most common is going to be the round cup. Depending on the part type and the shape, oval could make sense. It's going to give you more area. If you have kind of a longer but skinny part, it can give you more holding force by significantly increasing the area. Then there's also some rectangle options. You don't see those too much, but again, if the part and the application calls for it, it's a great solution. So building off of the shapes, there's also a lot of different types of cups. So the universal is going to be, as the name states, it's a pretty kind of cover-all basis, a general purpose cup. It's going to be pretty stable, and the one issue though is it's not going to have much height compensation. So your universal cup you can see here, there's really no accommodations for any adjustment in the Z height or the height of a part. The bellows type is where you can just have a single bellows, as you can see here in the top left. So that's going to give you a little bit of height compensation while still giving you a fair amount of stability. That leads into the multi-bellows. So while it gives you a lot of height compensation, it's not going to be very stable. So those cups get very wobbly, we'll call it, and the part can kind of float around as you move it from point A to point B, which could also cause issues where you break that seal, you lose that differential pressure and that vacuum condition, and you'll drop the part. So these are great where you need that height adjustment, but you just have to be wary of the applications and the accelerations and decelerations that you are applying to it. There's also flat cups, deep or D-shaped, which are for spherical or curved objects. Same thing with the flat concave. Those are going to be for slight curves or parts that are contoured. So those two aren't going to be used for flat surfaces. As there's a bunch of shapes, there's a bunch of types. There's also a lot of suction cup materials that are going to be well suited for different applications. The most common is polyurethane, so that's just going to be a strong, versatile solution. Silicone is going to be great where you need a large, high temp application. It can withstand much higher temperatures. It can also be FDA approved if you're handling food or things like that. And it can also be conductive, meaning that it can help discharge static electricity if you're, say, handling circuit boards or something of that nature. That is, that's susceptible to static. There's a HNVR. Those are, a very durable option. They're going to be great with oil and in a more wear-resistant application where maybe the part you're handling is abrasive and it can create a lot of wear on the lip of the cup. Those are also going to be mark-free, meaning if you're handling, say, glass, it's not going to leave that smudge. So it can be a great option in those kind of environments. There's thermoplastic polyurethane. Again, that's even better mark-free capabilities, but it's a harder material, hence why it doesn't really leave that smudge. So it's going to be a little bit more difficult to get a good seal depending on the surface finish of the material that you're handling. There's also different durometers. So durometer is going to refer to the hardness of that cup. The softer the material, the more it's going to conform to the surface. But it's going to wear quicker. Where the harder the material, it's not going to conform as well, but it could potentially last a lot longer. Again, there's a lot of options. If there's ever a doubt, just please reach out. We'll be happy to test it out for you and find the best solution. There's also a lot of accessories, so different ways to mount the cups, different fittings. There's something called Pi Save, which are these devices down here just to save energy and kind of shut cups off, if you will, when you're not using them, or save energy. There's also some level compensators, which are here, and those are going to give you a greater range of height compensation in the z-axis. So instead of having maybe a multi-bellows cup, you can use a level compensator, then use like a universal cup to still have good stability while still having some level compensation. And so that's here. Then also here's another example with the more external mechanical spring. So moving past suction cups, there's also foam tools. So foam tools can be a great solution for like the end of arm, or I'm sorry, for the end of a robot, for the tooling on the end of a robot. The cups are going to be well suited for more flat, smooth surfaces where the foam is good for irregular surfaces. As you can see over here in this picture, it's handling multiple cans at once with those odd shapes, and it can still create a good seal. The foam tools are always going to have some air leakage, but they're a very flexible and I'll say robust option when they're needed. You can also build systems with foam tools that include like check valves and other options. So it's a great option to have at your disposal if needed. So now that we've gone through some of the more common devices and some of the theory behind vacuum, once you need to design a system, you really need to start with the object being handled. So, how big is it? What's its shape? What's its surface like? Is it porous? Is it, dirty? Is it clean? And then some of the more process considerations are, what's going to happen in an emergency stop scenario? Is there static electricity considerations that you have to take into account? Does it need to be food safe, mark free, etc.? So there's a lot of things to take into consideration. Again, there's a lot of options out there because there are so many ways to use these and so many applications. But ultimately, you always want to start with the force equals area times the vacuum level. So based on the object you have, how much force do you need to hold it? But I will say that while that equation is simple enough, it's only theoretical. So that's in a perfect world with zero leakage, zero issues, zero things to consider. It's just a perfect seal. That's where this comes into play. You always need to account for some kind of leakage. For instance, if you're handling like a glass sheet, you're really not going to have much leakage. But if you're handling a very porous cardboard box, you can also have air actually evacuate through the box wall itself. So you have to account for even more vacuum flow through the material. So you can see that here. It's called permeability. So that's something that we often run into when handling, I'll say various parts of that nature. And it's just something you want to make sure is accounted for, or else you're probably going to be dropping parts. Another big consideration to make while designing a vacuum system is whether or not you want it to be centralized or decentralized. So the centralized solution is going to be what you see on the left here. It's a single vacuum source that feeds multiple cups or multiple tools that are doing the work and holding the part. So these are going to be easier to install. They're going to include fewer parts. They could be a little bit lighter, a little bit simpler as far as the installation goes and the design goes, and have a lower initial cost. But they're going to use more energy, and they're also much harder to troubleshoot. If something goes wrong, if one cup fails and creates a seal to where this system is leaking to atmosphere, none of the suction cups are going to create a seal, which can also be a safety issue. So it's just a big consideration where it's kind of all or nothing. All the cups or all the tools have to be working together, all have good seals for the system to work. Whereas the decentralized system, that's where each individual cup has a small venturi pump built into it. These can have faster cycle times. That's because each cup has a much smaller area. Each tool has a much smaller area in the cup to evacuate. So they can quickly evacuate the air, create a good vacuum scenario, and handle the part. They're more energy efficient as well. So just a bunch of small pumps instead of the one big one that's drawing maybe a lot more air. They're very flexible. They're very modular. They're much safer, since each cup is kind of a fail safe or a backup to its its partner. if one goes down for some reason, or if one gets very dirty or clogged, the other ones can still apply vacuum and hold force to handle the part. They're also easier to troubleshoot since each one is its own little system. You can quickly figure out which ones are working, which ones are not working. I will say these have a higher initial cost though, being that each one does have its own pump and it can add some weight, and it can be a little trickier to install because there's more parts and more things that go into it and more points where you may want to measure vacuum with the vacuum switches. So, a little bit more goes into it, but typically it could be worth it in the end. And I will say more and more systems are going to be decentralized these days. It's much more common. Granted, the centralized systems still, do still have their place. So as you're designing your system, you also want to take other considerations into account, like the environment. Is it cold or warm temperatures? Is there moisture present? Is it a dusty or contaminated environment, like a sawmill? Or is it more of like a medical device environment or application where, everything's very clean. It's very easy to get good seals and not have issues with the cups, getting quickly worn, or creating bad seals. You also want to look at your cycle times. That's going to really drive how, what kind of a system you want, how big the cups can be, what type of ejectors you want to use, how quickly is the system going to excel and decel. Again, if you're on like a 6-axis robot, you can move very fast, but if you don't have the right cup, you can break that seal and drop parts. And then also, are you going to be in, we'll call it the perpendicular, orientation or the parallel orientation? We do recommend a 2-to-1 safety factor with your designs for perpendicular. As with the parallel, we're going to recommend a 4-to-1 safety factor. And then this chart down here is just showing you some of the different holding forces that each scenario can get at varying vacuum levels. So with a 35 millimeter cup at 6 inches of mercury, you can get 2.7 pounds of holding force, whereas if you have a 75 millimeter cup at 27 inches of mercury, you're at 45, 46. So you can get much different results depending on your cup size, your orientation, and then also the vacuum level. All right, that wraps up our vacuum training. Thank you all very much for your time. Just to recap, we covered vacuum theory, the parts that go into a vacuum system, some pros and cons of the different types of systems, and what goes into sizing it. If you have any questions about any of these concepts that we covered, or if you need support on an upcoming application, please reach out. All of our contact information is included. Thank you.